Hello guys, welcome again to this video. So from this video onwards we'll be trying to focus on how to prove the Euler's reflection formula. So it basically is that we have completed one half of our study of the gamma function. Basically we did all the fundamentals of gamma function, like we now know about the recursive definitions. We do know about how to do more problems, more integrals using the gamma function, different representations of it. We do know what happens when we have a real number argument. We know that what happens when we have a natural number argument and something like that, right? So to summarize our results from the previous chapters, which are literally a lot to take in. So the basic definition was basically gamma of n equals to 0 to infinity x to the power n minus 1 e to the power minus x dx, right? And to count on the basic definition, we extended it to find out the recursive definition, which was this: gamma of n is equals to n minus 1 into gamma of n minus 1, but remember this holds only when n is greater than 1. Then we also found out that for real numbers we can also have gamma of s plus 1 by a to the power s plus 1, where a is greater than 0, which I'm going to write as a information for this integral, which is 0 to positive infinity e to the power minus x, basically xa, which is ax, and x to the power s dx. And what we should have here is s should be greater than minus 1 and a should be greater than 0. So equipped with these two conditions, this equation always holds. Well, obviously s and a are real. This need not be said because we are not really dealing with complex numbers right now, but when we will be trying to prove the Euler's reflection formula, we might be dealing with something completely new, which is in the field of complex analysis. But it is required because there is no known method for proving the Euler's reflection formula using real analysis. There is none, and the most proficient way to prove it is by using contour integration, which is integration in the complex plane. So like we shall come to that in a moment. But before that, the Euler's reflection formula said that gamma of s into gamma of 1 minus s was equals to pi by sine of pi s, right? Where 0 less than s less than 1 and s was a real number, right? In general, s belongs to 0, 1 open interval, right? That is this. So this could be what our results have been so far, which we are going to use, but our main goal would be to find out about how to prove this integral. Now in the previous video I had told you about little something on how to prove this kind of integrals, or how we are going to begin proving them. So let us see. So let us first write down the integral representation for gamma function. So what I'm doing is I'm trying to write it elaborately because I want you to follow these notes as well when you are going to solve a problem, because you would need this kind of statements to support your actions that will follow up in your answer sheet. So this notes here or this video here basically gives you a complete note for writing a particular answer or particular theorem or explaining something particularly. So that specific question would have the complete answer to it in this note or in this video, because what I'm trying to do is I'm trying not to miss any steps at all, because then you would know what to do if you were not to miss any step at all. But of course, if you were explaining this to someone or just doing a casual warm of proof, you might skip details, but you should know what to write or what the teachers would expect when you were to write a proof or something, or maybe solve an integral, solve a problem. So this is essential. So we first need to write down the integral representation for gamma function, and specifically for these two quantities. So let me just write them down. Zero to positive infinity x to the power s minus 1 into e to the power minus x dx, right? Well, in both the cases we will have s belongs to 0 comma 1, and for the other one what we are going to do is we are going to change the variable, because we do not really want to represent both the integrals in terms of a single variable, which is obviously valid but not valid when we are multiplying those two integrals, because these are separate integrals. So the only way they can be multiplied together is when the variables are independent of each other. That is, we will have y to the power, so like this thing here, into e to the power minus y dy. So gamma of 1 minus s is basically 0 to positive infinity integral y to the power 1 minus s minus 1 e to the power minus y dy. This will give us 0 to positive infinity e to the power minus y into y to the power minus s dy. So this would be a representation for the integrals. Now what happens if we multiply them together? Let's see. So gamma of s into gamma of 1 minus s. Now this would be a double integral like this. So let me write it down below it so that I get more space. Now note that in a double integral, the order of dy and dx is very important, and it also denotes which is the inner integral and which is the outer integral. So since I have written dy dx here, this means that the inner integration is for y equals to 0 to infinity, and the outer integration is for the variable x, which is x equals to 0 to infinity. This is very important. Now what we want to do here is as follows. We want to keep the y integration outside like this. What we want to do is we want to set y equals to 0 to y equals to infinity outside. We take the variable of y here, and we want to keep everything else inside the x integral for now on. X equals to 0 to positive infinity, x to the power s minus 1, and we also have e to the power minus x, we also have y to the power minus s dx dy, right? Now why are going to do that? Because you see, what we are trying to do here is something like this. Notice, because well, obviously we need to make some substitution, and it is understandable that the substitution should be such that it makes the double integral into a more simpler form, right? We want to have a more simpler form, and this inner integral is the key to that. Now what is that one thing that we should substitute so that it may be a better version? Now notice that x to the power s minus 1 y to the power minus s is just equals to x by y to the power s minus 1 multiplied by y to the power minus 1. So it seems that x by y could actually be a good change of variables if we could. So set u equals to x by y keeping y fixed, and this would give us du equals to dx by y, and what we will get here is basically this. Let me just rename the integral as I. So let us say we are evaluating the integral I, which is the double integral, and we have y equals to 0 to infinity e to the power minus y, and the inner limits. Now the inner limits will still be from 0 to infinity because y is just kept as a constant and we are just evaluating the limit for x, and it will turn into something like this: u equals to 0 to infinity e to the power minus uy into u to the power s minus 1 du dy, and this will be our resulting form. Now obviously this is a form which we are trying to understand if this is a better form or a worse form, but well, obviously this would give us the required result we need, right? So we will be doing this up to this part only for this lesson, and in the next video I shall continue from here onwards about what to do next and how to evaluate this double integral. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.